tension in a string and pulley systems involving blocks and pulleys and strings, and application of Newton's second law for the same, application of free body diagram concept in all of these, etc. Okay, so these are some of the things that we've been discussing. So we will start today's session with an example or two of the application of the same. So this is session number 5 of Newton's laws. Okay, so far we have discussed about the free body diagram method and the common types of mechanical forces like normal reaction and tension, and also the application of free body diagram method in pulley based systems. So let's start today with an example of a pulley based system. So just try out this question. This is for all of you to work out yourself. So we have a system like this, like a double inclined plane. With a pulley attached at the top. And a string going around like this. Okay, so there's a block A attached on this side and another block B attached on this side, and this angle is alpha and this angle is beta, and these are both smooth surfaces. Okay, so given that alpha is equal to 30 degrees and beta is equal to 37 degrees, and mass of the block A is, let us say, 4 kgs, and mass of the block B is, let us say, 5 kg. So this system is released from rest with the thread tight or taut. You have to find the accelerations. So start this question. Assume that the thread is light and inextensible and the pulley is a standard pulley, so it is frictionless. It's a smooth fixed pulley. Also take acceleration due to gravity to be 10 meters per second square. So let's begin by understanding the distribution of forces in the system. So you can see that the components of weight you can divide like this. Okay, this kind of distribution. Then of course there will be tension in the string, which is uniform in magnitude at all the places because it's a massless thread. And then there will be normal reaction on this block, normal reaction on this block. So the direction of acceleration will depend on which one dominates. So you can see over here that this value is 5 into 10 into 3 by 5 because the values given to us were like this. Okay, so this is 30. Whereas on the other hand, on this side, the force that is trying to pull the system down is 20. So this one dominates. Okay, so because this force is larger than this force, okay, therefore B will accelerate down the incline and A up the incline. So the directions are going to be like this. A will accelerate up the inclined plane and B will accelerate down the inclined plane. Because they're tied by a thread, they will have the same magnitude of acceleration. E. Yes, it was given. Okay, so now use the free body diagrams I made and calculate the magnitude of the acceleration. Yes, so anyone got the magnitude of acceleration? Yeah, the free body diagrams you require are here. So you have to just use these now. So for the block A, you can see the equations you will get are like this. T minus mg sine alpha is mass into acceleration. So this equation is T minus 4 into 10 into half is equal to 4e. So T minus 20 is equal to 4a. This is your equation 1, let's say. And of course, along your perpendicular direction, normal reaction is balancing the weights cos component. So that when you work out, it will come out to be 20 root 3 newtons. Now similarly for B, yeah, that's correct. Kunj, your answer is correct, Kunj Modi. G by 9 you should get, or 10 by 9, so that's 1.11. Okay. Now similarly for the block B, your equation will become something like this. The net force downwards will be the weight's sign component minus tension. So that should be equal to mass into acceleration. So T minus 5g into sine 37, so 3 by 5 should be equal to 5a. So we should get, my mistake, this we reverse. So this is 5g sine 37 minus t should be equal to mass into acceleration, that's 5a. So this will become 30 minus t is equal to 5a. So these are the two important equations, equation 1 and 2, which were written here. The other two equations are just supporting equations, which are just giving us the normal reactions, which are not really required in this question. But nonetheless, okay. Now you solve these two equations, then you will get the acceleration as 10 by 9. Yes, Hitanshu, that's correct, or 1.11 meters per second square. Yes, that's correct. 10 by 9 is the correct answer, or 1.11. So you can add the two equations, and you will get 10 is equal to this. So this becomes your final answer. Okay, so hope this question is clear to all of you. Now let's move on to the next one. Now we'll do one more practice question where we'll discuss a couple of more things that can be asked in a situation like this, in a system involving a pulley and blocks and a thread. Apart from acceleration, what else can be asked? Let's understand that. So this is again a smooth surface. So this time given to us that mass of the block A is, let us say, 6 kilograms. Mass of the block B is 4 kgs, and take G as 10 meters per second square. The thread is massless, okay, and the pulley is also smooth and massless. So the disk of the pulley also has negligible mass compared to the mass of the blocks. So we want to find first of all the acceleration of the blocks. That's the standard thing, but also the tension in the thread. And we also want to find out, now this is an additional thing that can be asked, we want to find out the reaction force acting on the pulley, okay, applied by the clamp, okay. The pulley is clamped to this corner, so there is some kind of reaction force acting between the clamp and the pulley. So how much reaction force is the clamp applying on the pulley, that we have to calculate. So we'll see how to work out the third part. It will come from the free body diagram of the pulley, so we'll discuss about that also. But first of all, find out the acceleration and the tension. That will come from the standard free body diagram. So just work this out. Yes, Rishi, that is correct. The value of acceleration you got is correct. Very good. Now you have to just substitute that acceleration in the equations to get tension also. So just substitute the acceleration you got Rishi in the equation. Yes. No, टेंशन 40 न्यूटन नहीं होगा बेटा. आपने जो इक्वेशंस लिखा है ना टू गेट द एक्सेलरेशन, substitute the value of a you got in that. Ruk sir, your answer is not correct unfortunately. Okay, so let's once again understand the forces acting on each of the blocks in the system. Yes, Kunj, your answers are correct for acceleration and tension. Now you make the free body diagram of the pulley to understand the reaction force. Okay. So here let's understand. First of all, let's understand the tendency of motion. So this will have a horizontal acceleration, the same in magnitude as the vertical acceleration of this one. So that acceleration is E, let's say. And then there's a uniform magnitude of tension T acting everywhere in the thread. Okay. Yes, Rishi, your answer is correct. Now for block E, you can see the free body diagram. The forces are tension, normal reaction, and weight. Okay. And the block is having a horizontal acceleration like this. Mass of A is given to us as 6 kg. So tension will be equal to mass of A into acceleration. So this equation will become T is equal to 6A, and normal reaction will balance the weight, which is 60. So this is the important equation for us. Now similarly for the block B, you can see it's an even simpler situation because only two forces and has a downward acceleration of E, and mass of B is given to us as 4 kg. So we have weight minus tension is mass into acceleration. So we have 40 minus T is equal to 4E. So this is our second equation. So solving the two equations, if you do equation 1 plus 2, you will get 40 is equal to 10A. So we get the acceleration as 4 meters per second square. That's the first part. Then substitute this in equation 1 and you will get the tension equal to 24 newtons. So this is your second answer. Now for the third part, you have to make the free body diagram of the pulley. Yes, Rishi, your answer is correct. So let's look at the forces acting on the pulley. So there are two tensions acting on it. The horizontal tension acting at the top like this, and the vertically downward tension acting like this. Of course, it's massless. So the pulley's own mass is tending to zero. M is tending to zero. Okay, but it's in equilibrium. Okay, the pulley is at rest. So that means what should happen? The net force on it should be zero. So these two tensions are pressing it against the surface, against the clamp. So the clamp will be applying a reactionary force, which will be in this sort of direction. Okay, just a minute. Yeah. So the clamp will be applying a reactionary force which will be in this sort of direction. Okay, so R here is the reaction force of the clamp, okay, which balances the vector sum of the tensions acting. Okay, so your vector diagram will look like this. This tension T and this tension T, they're at 90 degrees. They should be balanced by this reaction force. Okay. So you can see that the reaction force will have a magnitude of T root 2 and act at 45 degrees like this. So this is how it balances. Yeah, you can use Lami's theorem, but this one is actually pretty simple ना. ये देखो, ये दोनों टेंशन का वेक्टर सम 90 डिग्रीज पे ना, तो इनका वेक्टर सम कैसा है, ऐसा है ना, टी रूट टू. सो इसको कैंसिल करना है ना, द रिएक्शनरी फोर्स हैज टू बी टी रूट टू and exactly opposite to this. So no need to use Lami's theorem here, right? It's a more direct case. Okay, so hope this is clear. So these are some of the other things that can be asked as questions in pulley-based systems. Okay, to find out the tension in the thread and the reaction force at the axle of the pulley or the clamp of the pulley, whatever be the case. Okay. Now we move on to the next level of conceptual understanding, which is dealing with systems of pulleys, okay, or systems with multiple pulleys. Okay. So we'll start with an example where we have a system of two pulleys, but gradually we will move on to more complex examples. We have one pulley which is clamped over here. I have another pulley somewhere here. So again, both pulleys P1 and P2 are smooth and massless. Okay. The thread is massless. Okay. And as usual, inextensible also. It cannot extend. That's always the case. We are always considering inextensible threads here. So given, so this information is given. Now the system is released from rest with the thread taut at time t equal to 0. Okay. Now the first thing we have to do here is that if the block B descends through a distance of x, then how much will A displace by in the same time? So in the amount of time that the block B comes down by distance x, we have to find out how much the block A would have moved by. Okay, so that is the first part of the question. Second, we have to find out the ratio of acceleration of A is to acceleration of B. Okay. And third is we have to actually calculate the values. Okay, so just take down the question first. We'll discuss in detail. Okay, so let's start by understanding the first part. So to understand the first part, we will compare the system at two different times. Okay, write down the question first fully, and we'll come back to the solution. Okay, so let us understand how to work out the first part, the relationship between the horizontal displacement of the block A and the vertical displacement of the block B. So this is actually called something called a constraint relation. Okay. So what is happening is that if this is the situation at some time t, let's say, okay, and after some time delta t, what has actually happened is that this block is no longer here. It has moved away from here. A is now moved like this by some displacement SK, which we want to find out. Okay. And similarly, this block and pulley are no longer here. Okay. But okay, so this whole part of the system has moved from here. Okay, so it has moved down by a distance x. Okay. So now what we can see by comparing the two diagrams is that when B moves down by this distance x, in comparison from here, how much thread length it is pulling. See, it is moving by distance x. So it is pulling x plus x 2x amount of thread length. And how much thread length A is releasing, whatever this S is. Yes, so that answer becomes 2x. Okay. So that when B displaces by SB equal to x downwards, okay, the pulley P2, which is attached to B, pulls 2x length of thread with it. Okay. So what will happen as a result of it? A will displace by SA equal to 2x to release the 2x length of thread. Okay. So this whole process that we have done here, this is called constraint relation. That is, the ratio of the displacements is like this by thread length conservation. We are saying that the thread length is remaining constant. So that is why when B pulls 2x amount of thread, A has to release the same amount of thread. Why? Because the total length of the thread is conserved. So the equation that we are getting from it, that A's displacement is double the magnitude of B's displacement. That relationship is called the constraint relation. So just make a note of this for you. No, so that's why the answer to the first part, that's correct, Rishi, that the displacement of A will become 2x in the amount of time that displacement of B is x. All right, so now we can understand, once we have got the constraint relation between the displacements, we can also develop the constraint relation between the instantaneous velocities, let's say VA and VB, and their instantaneous accelerations, acceleration of VA and acceleration of. So next we will see SA is equal to SB, sorry, 2 times SB. This is the constraint relation between the displacements of A and B. So now we can differentiate that. So rate of change of A's displacement, 2 is a constant, so will become 2 times rate of change of B's displacement. So the instantaneous velocity of V at any instant will be 2 times the instantaneous velocity of B at the same instant. So this is now the constraint between the velocities. And differentiate this once more. So this will give you the relationship between the accelerations. This is okay. So you can see the second part's answer, ratio of their accelerations will be 2 is to 1. Or if acceleration of B is equal to A, then acceleration of A should be 2. Okay. So in any system of pulleys, this becomes very important. This process of constraint relationship between the accelerations of the blocks involved, which will come by conservation of thread length. This becomes very important. Okay, now next thing is we want to find out these accelerations in actual magnitude and value. Okay, so let's go back to the original diagram and understand the forces which are acting on the blocks. This is the diagram, and let's pick up the values also. Okay. Now, first of all, you can see that there is a uniform tension because the thread is massless. So the magnitude of tension is same everywhere. And secondly, we can see what we just discussed, that they don't have identical accelerations, they have different accelerations, such that if we take the acceleration of B as A, then the acceleration of A is in fact twice of A. So we have acceleration of A is 2 times acceleration of B. That is our first equation in fact, which is what we call the constraint relation. Now let's come down to free body diagrams. So A's free body diagram is pretty simple. There is just one horizontal force and two vertical forces, and this combination is giving me an acceleration of 2A. So the equation we will have for A is that T is equal to mass of A into acceleration of A. So we'll write that as T is equal to 4 into 2A, because we'll substitute acceleration of A as 2A. So T is equal to 8A. That is our second equation. And of course, we also have normal reaction is balancing the weight. So that is not going to be of much consequence here. Okay, the main thing is going to be this equation. Now let's pay attention to B. Now B situation one has to be a little careful about, because B has the pulley attached to it. So we have to include the pulley, which is massless, but nonetheless the forces acting on the pulley are acting on B indirectly, because the pulley is attached to the block B. So there are two vertical tensions acting on B. Okay. And B's own weight. So this is the situation of block B, and B has a downward acceleration of E. So we have weight minus 2T is equal to mass into acceleration. So this becomes, the weight is 20 newtons minus 2T is equal to 2E. So this becomes the third and final equation. Okay. So we had variables A1, A2 and T, three variables, and we've got three equations. Okay. So now just substitute the value of T from here. Substitute T equal to 8A. So we'll get 20 minus 16A is equal to 2A. So A comes out to be 20 by 18, or 10 by 9, or 1.11 meters per second square. So therefore acceleration of A, which is 2A, is 20 by 9, or 2.22 meters per second square horizontal, and acceleration of B is 10 by 9, or this much vertically downwards. So these become our answers. Okay, so I'll systematically take you through the whole solution once more, but just note down the equation solving first. Okay, so let's just take a look at constraint relation concept once more. Then we'll come back to this. So make sure you understood this first step, the relationship between their displacements. Okay. And then from that, the relationship between their accelerations, which will come by differentiating that. And then finally, the solving of the equations. Okay, so hope this question is clear in all aspects to all of you. Now, this kind of concept is very important in Newton's laws of motion for both JEE mains and JEE advanced type of questions. So we'll practice quite a few. So let's look at the next one. So this time our system also involves an inclined plane. So this is a fixed inclined plane of 30-degree angle, smooth. Okay. Now the inclined plane has a pulley attached and a string going round. Second pulley like this now. So again a fixed ceiling. So this time in this example, given that theta is equal to 30 degrees, acceleration due to gravity is 10 meters per second square. Mass of the block A is suppose 5 kilograms. Okay. Now first part, if the system remains at rest, that is in equilibrium, when released with the thread taut, find the mass of B. And secondly, if instead mass of B is, let us say, 2 kilograms, then find accelerations of the blocks A and B. Okay. Again, both pulleys are massless, smooth and massless. The thread is light and also inextensible. Okay, so just try this question out, people. Use the free body diagram concept to work out the first part. And from that, you will also get an idea in the second part what exactly is happening. When we change the mass to 2 kg for B, Mass of A is remaining 5 kg for both the parts. Yes, Ruksar, your answer for the first part is correct. So far, one person has got the first part correct. Rest of you can work out the first part at least, I'm sure. It will just apply the condition that both the blocks A and B should be at rest. So the first part for equilibrium, basically you want acceleration of A should also be 0. Acceleration of B should also be 0. Okay. So you can just understand the forces acting. So mass of A is given as 5 kg. Mass of B we want to find out for this condition that this one's acceleration is also 0. This one's acceleration is also 0. So just balance the forces. So I'll just give you a hint by drawing the components of weight here. This will be 5g cos 30 degrees and this will be 5g sine 30 degrees. And the normal reaction here. This is MPG. Okay. So for A we'll have the equation that tension equals to 5g sine 30 degrees. So that is 5 by 2g. And for B we have the equation that 2t balances MPG. So just compare the two equations. You will get that for equilibrium. So this is the condition for equilibrium. Now second part of the question, you are keeping the mass of A as 5 kg only, but changing the mass of B to what? 2 kgs I think, right? Yeah, 2 kgs. So you have to find the acceleration of A and the acceleration of B. So you can see it's becoming a lot less. So this time B will be going up and A will be coming down. Okay, Kunj, what are the directions of the accelerations? Which one is going up and which one is coming down? Yes, that's correct. Okay, so because B's mass is lot less than what we calculated in the first part, so one thing we'll immediately understand here is that this time the block B will be going upwards, and therefore the block A will be accelerating down the inclined plane. Okay. So first thing we have to understand constraint relation. Okay. So constraint relation वो कैसा आएगा? If B makes a displacement of x upwards, what happens? It releases 2x thread. It will release 2x amount of thread length. Okay. So immediately what will happen? A will make A will pull 2x amount of thread. Okay. So SA will become 2x. So SA is twice of SB. Okay. So from that we get this. So this is our constraint relation, in fact. So this is the first thing we have to understand over here. Okay, rest is all free body diagram, of course. Okay, so next from the free body diagram of A, you can see that there is 5G sine 30 degrees tension normal reaction, but more importantly, acceleration of A, which we can write as 2A. So if acceleration of B is A, acceleration of A will be written as 2A. So we'll use these values. Okay. So for A, we have the equation 5G sine 30 minus T is 5 into acceleration of A, or 25 minus T is 5 into 2A, or 25 minus T is 10A. So that's our second equation. Okay. And now likewise for B, remember B has the pulley attached to it. So there are the two tensions acting on it. And its weight is 20 newtons. Its mass is 2 kg. 2g, we can write it like this. Okay. And it has an upward acceleration equal to A. So for B, we have the equation 2t minus weight is equal to mass into acceleration. So we have 2t minus 20 is equal to 2. So this is the third equation here. Now you have to solve these equations to find solve for section of A. Okay, so you can just take this equation and divide it by 2. So it will become t minus 10 is equal to 8. So this is the third equation. And take this equation directly. 25 minus t is equal to 10a. That's our second equation. Add the two equations. So you get 15 is equal to 11a. So we get a as 15 by 11. Or that is, okay. So understanding now what we are doing here is we are dividing this equation by 2. Equation 3, we are dividing it by 2. So we are getting this. So from that we are finally getting acceleration of A is 2a. So acceleration of A is 30 by 11, or that is approximately 2.73 meters per second squared down the incline. And acceleration of B is A. So 15 by 11, or approximately 1.36 meters per second square up vertically upwards. So these become my final answers. So hope the equation solving part is clear to all of you. Kunj, have you checked your calculations? Okay. Okay. Okay, now next concept we look at in Newton's laws of motion is a new definition or a new term for us, something called an inertial reference frame. And its opposite, which is a non-inertial frame. So in general, one should understand that any observation about the motion, or basically that is the kinematics of a body or a particle, okay, is always made with respect to a reference frame. Okay. So for example, the displacement, velocity, acceleration, etc., all are observed or measured, whatever, with respect to some reference frame. Okay. So a reference frame is nothing but a system of coordinate axis. Okay. So now, if two different frames are moving with respect to each other, okay, then as you know, observations made from each frame are different, okay, because they are relative to that particular frame. So this is the concept of relative motion in kinematics. Just make a note of this statement first, then we'll see what is inertial frame and what is non-inertial frame. Yes, Om, you have some question, better? Okay, okay, no problem. Okay, so just write this down. Okay, so let us illustrate this point about reference frames with an example. Just finish writing this down first. Okay, so for example, we have a situation like this where, let's say, we have, let's say, a bus which is moving at a speed of, say, 12 meters per second in this direction. Inside that bus, we have a fixed object O, and a person standing inside the bus also at fixed to the bus A. Okay. Then we have the opposite side, car coming from this side at a speed of 20 meters per second, and the person B inside the car. Okay. And we have a person C stationary on the road. Okay. So the object O is fixed to the bus. What is the speed or velocity of the object O as seen by A, a person inside the same bus at rest with respect to the bus. Person in the car shown, and C, the person at rest with respect to the ground frame. Okay. So just work this quickly out and tell me. Give me the answers to the three parts A, B, and C in serial order. You can just type out the numerical values in meters per second, whatever you will get. Should be fairly easy. Yes, very good, Kunj, that's correct. Yes, Om, your first part is correct. Yes, correct. Second part also. Okay. So if we are just talking about speed, the answer for this will be, this guy will see the speed to be 0. This guy will see the speed to be 32 meters per second. And this guy will see the speed to be 12 meters per second. Okay. But if we are talking about velocity and we involve some kind of coordinate axis, so this is C's coordinate axis, this is A's coordinate axis, and similarly, this is B's coordinate axis. So x-axis is like this only. Then the velocity as seen by this guy will be this null vector. The velocity as seen by the second guy will be minus 32 I cap. So he'll see it going along the negative x direction. Oh, sorry, plus 32. See, coming along the positive x direction only. Okay. And the velocity seen by the third guy will also be along the positive direction only, the plus 12 I cap in meters per second. Okay. But only in terms of direction, this guy will feel that it's moving towards B. Okay. Whereas this guy will feel that it's moving away from himself. Right. So this is the very simple application of relative motion concept, which I'm sure you have studied in kinematics. Okay. The concept of relative motion, that the displacement of a body A with respect to another body B is the difference of their vector difference. Similarly, the relative velocity is this, and the relative acceleration similarly is this. So these are the equations of relative motion. Okay, on this side, we have the motion of A relative to B. And on this side, we are writing it in terms of motion of A and B with respect to the common ground frame. Yeah, so that depends on how you're defining the sign convention. No, if you're defining it according to whether you're coming closer, so it's positive, going away is negative, then it's fine. If you're defining according to the I cap, J cap, which I have shown, then it will be according to plus I cap and minus I cap. But if I'm talking about speed, it will never be shown with sign. Okay, now speed is magnitude of velocity, so it does not have plus or minus sign. When I show velocity, yes, there should be some algebraic sign. And I have written in terms of unit vectors, so both of them are along positive x-axis. Okay. All right. So now coming back to what is the significance of all this in Newton's laws of motion. So the first thing we'll understand is the definition of inertial frame. So what is an inertial frame? Inertial frame is a reference frame which is either at rest with respect to the ground frame, that is the Earth's surface, okay, or in uniform motion, that is moving with constant velocity and zero acceleration with respect to ground. Okay, so that is the definition of inertial frame. So obviously the opposite of that, the non-inertial frame, that is defined as something that is moving with acceleration. Okay, so hope the definition is clear to you. Okay. Now, the most important thing here that when observing the free body diagram for an object in any inertial frame, in any inertial reference frame, okay, we can directly apply Newton's second law as net force is equal to mass into acceleration. Of course, mass is fixed, okay, but for the observation of a free body diagram in a non-inertial frame, okay, we have to adjust the application of Newton's second law with the addition of something called a pseudo force. Okay, so this is a very interesting subject, the concept of pseudo force. And we run out of time today, so we'll discuss in detail the next time about pseudo force. But just to give you an idea, whenever we are in a non-inertial frame, our body experiences something called a pseudo force. Like when you are standing in a bus, which is initially at rest, and suddenly it accelerates forward, so your body feels jerked backwards, while there is nobody pushing you directly backwards. So it's not a force applied by some external agent, but because the bus accelerates forward, so it becomes a non-inertial frame. So your body experiences something called a pseudo force, which pushes your body backwards. Similarly, if you are in a vehicle that is moving and suddenly it brakes and it decelerates, then your body feels jerked forward. Now again, there's nobody pushing you from behind, but you just experience a force in the forward direction. Why? Because you're in a non-inertial frame, and any body in a non-inertial frame experiences something called pseudo force. Okay. Same reason why we feel uncomfortable in roller coasters, or if we step into a lift which accelerates downwards or upwards at a very high rate of acceleration. Again, our body experiences these kind of imaginary forces or pseudo forces. So we have to account for those when we apply Newton's second law in the non-inertial frame. Okay. So we'll discuss about this in detail in the next lecture, which is anyway coming up in this week. So in the meantime, you can complete questions from HC Verma. You can complete up to about question 20 or so from HC Verma, 20 to 22, something like that. And you can also do a bit of theory reading ahead if you like about inertial and non-inertial frames and pseudo force. But most importantly, make sure you revise the concept of constraint relation that we've discussed for system of Pulley today. And you will find a number of questions in HC Verma related to system of pulleys, multiple pulley systems with where you have to take constraint relation into account. So you can try out those questions. You can also start working out questions from your module exercises. Okay. So that's it for today's class, people. Wish you all the best.